Francisco here at the University of Montana. Welcome to our course, Math 595, Teaching Geometry from a Middle School Setting. So I'll weekly record at least one video, maybe two, to, I guess, maintain some face contact with you and feel like I've given you some direct instruction. Just a little bit about me. I'm here in the math department. It's a beautiful day out on campus today. Those of you who've been here will recognize the M above campus, and of course I'm right around the corner from the main hall building on campus, so right on the main oval of campus. So it's a little bit about where I'm at and my office, I guess, and a view of a beautiful summer day outside. So let's go ahead and get started. I'll switch over here to our first video lecture, and I guess for this week all I'm really concerned with is that I introduced the course and this notion that there are really three geometries in K-12 mathematics. I think this is of interest to teachers because from a mathematician's standpoint, geometry in the K-12 which always receives a single name, is really three different perspectives on this study of shape. All right, so I want to talk to you about the three geometries and briefly define them: synthetic, analytic, and transformation. And then I want to spend most of my time just on a comparative example of a simple one. And your content homework for the week will be to do something similar to the comparative example. And then I do also want to say a word about technology, since I'll be using GeoGebra pretty extensively in the course, and talk about how GeoGebra makes real each of these, or I should say accessible, each of these three different types of geometries. So the teaching of geometry in K-12 mathematics can be loosely categorized into three different perspectives in which mathematical objects are visualized or studied. And these perspectives are synthetic geometry, analytic geometry, and transformational geometry. It's important that you make a distinction between the three, because these are going to be the three of the 5 weeks of the course will be dedicated to each one of these perspectives and doing a little bit of content work in each of these perspectives. Synthetic geometry, what is it? Synthetic geometry is sometimes called axiomatic or I guess pure geometry. It's the study of shape using the axiomatic method, and it begins with a set of givens. Usually these are assumptions or axioms, and then it builds from assumptions results, theorems usually we call these, sometimes lemmas, using only the tools of logic and the tools of picture drawing, where we think of tools to draw the primitives, which are points, lines, and circles. So this would be, for those of you who had a classic geometry course in high school, these would be the classic compass and straight edge constructions. So you're engaging in synthetic geometry if you're proving things, usually from axioms, or showing logical conclusions, or where you are actually constructing things, say like an angle bisector or a perpendicular, a segment perpendicular to another segment. So those are the types of things we do in synthetic geometry. Of interest, I guess, in synthetic geometry to the K-12 mathematics, of course, would be this idea of proof, which seems to take front and center in our study of geometry when it's conducted synthetically. Analytic geometry, though, is another view that we give students in K-12 mathematics and geometry. It's sometimes called Cartesian geometry for Descartes, the person who gave us the coordinate plane. Or you could call it the coordinate geometry. Sometimes you hear it referred to that way. But this is just the study of shapes drawn on a coordinate system. Usually, we're more interested in this case, in equations that relate geometric objects. So things like the equation that relates, that gives the distance between 2 points on a coordinate plane, or the equation of a line on the coordinate plane, or the equation of a circle on the coordinate plane, or for those of you who teach maybe a high school algebra course, equations of conic sections on the coordinate plane. Lastly, one important aspect, especially in the middle school, it also comes up in high school and becomes an important tool in high school, is the idea of transformational geometry, and that's the study of shapes understood according to the size and shape preserving actions of reflection, rotation, and translation, as well as the shape preserving action of dilation. So these transformations, ways that we take a shape and move it somehow, using what are known as isometric transformations, the ones that preserve shape and size, which are reflection, rotation, and translation, as well as the non-isometric one, the one that doesn't preserve size but does preserve shape, that's dilation. Okay, well, let's take a look at a comparative example. So what I want to do is just contrast these three systems or ways of thinking by observing, or I guess studying, a single object, and that's an equilateral triangle. So let's suppose, well, let's define it first. An equilateral triangle is a triangle that has three sides of equal length. So from a synthetic standpoint, what we could do is we could build an equilateral triangle using a compass and straight edge. From an analytic perspective, we could try to figure out this problem. An equilateral triangle has vertices at 1, 2, and -5, 2. What are the possible locations for the third vertex? And then from a transformational symmetry standpoint, we could try to identify the line and rotational symmetries of an equilateral triangle. So let me switch over to my desk and let's do a little bit of math. All right, so here we go. Oh, I have to turn around to do this, so sorry about that. I also need a little paper. Okay, well, let's try the first. Can you see that? Yes, you can see that just fine. Let's try the first task, and the task here is a synthetic task, and what it's meant to do is, well, let's do it this way, I guess. That'll work fine. So here's our task. Construct an equilateral triangle. Okay, well, so what we're allowed in typical synthetic geometry constructions are something to draw lines, something to draw circles, and something to draw points. So we are going to do just lines, circles, and points, and let's see if we can use logic to deduce how to do this. So I guess what we need to start with, if we know that all three sides of an equilateral triangle are of equal measure, we could just start with a single side, right? We could start with a side. Let's say that's the first side of our equilateral triangle. I don't know, let's give these points at the end of the sides a point A and a point B. And then what we're after is a point C, either here or here, I guess. That would be the same distance, A to B. Let's call that distance, I don't know, D. So it would be a distance D from A and a distance D from B. And it has to be the point that actually satisfies both of those conditions in order for it to be equilateral. So what it seems like, we could play around with this idea of, well, marking off a little piece of the ruler and trying to sort of replicate where it's going to be, but right away I can kind of see, well, what that's going to do is basically give me a collection of points that are all that same distance away, which means they're on a circle, because of course a circle is a collection of points that are equidistant from some center. So I'm going to set my compass to be that distance away from B, I guess distance D, opening. I'm going to put my center at A, and I'm going to ascribe a set of points. If I call this distance D, these points are all points on this arc are what? Distance D from A. Would you agree? Since that distance hasn't changed, anything on that is that distance away from A. And what we're looking for is the one on here that's exactly that same distance from B. So let's do the same thing, putting our point now at B and scribing out an arc. And be careful here. I want to make sure this is understood that those are all distance D from A. So let's let this one be, let's say, all these points on this arc are a distance D from B. So it sort of seems to make sense logic-wise. If these are all a distance D from B and these are all a distance D from A, then that one point right there, let's call it C, that's the point that satisfies both of these conditions. It's the same distance D from A as it is from B, which means that that's the point that will form an equilateral triangle. And so I'll go ahead and draw it in just to see if it makes sense. And of course I can use my compass to measure to verify. Sure does seem like it is. Seems like it is. And I'll just write a conclusion down here. Since C is on both arcs, it is what simultaneously distance D from A and a distance D from B. So I guess triangle ABC must be equilateral. And that would be an exercise in synthetic geometry. You know, we start with givens, primitive notions of how to draw a circle, a line, and a point, and we use logic, an argument of logic, to arrive at a construction that would work. One thing I should point out is, of course, this is a very precise I guess, drawing, but, if we were to get out some sort of atomic ruler and measure this, of course, this is probably not a perfect equilateral triangle, depending on how closely we measured it. So what's important here is really not necessarily the object that we construct, but the logic of the construction, which is really, I think, one of the neat things about synthetic geometry. It's this idea of constructing or creating new things, and they're ideal new things, things that probably aren't really what they say they are, using logic and very primitive assumptions, things to draw a line, a circle, and a point with. Okay, so we have an example there of synthetic geometry. So let's try an analytic problem about equilateral triangles as well. Suppose we have an equilateral triangle with vertices at 1, 2 and negative 5, 2. What are the possible locations for the third vertex? All right, let's try that one. Okay, so we're in a coordinate geometry setting. We're still talking about equilateral triangles, but the flavor is going to change quite a bit here. So I'm going to draw a little picture of what we have. If this is my x and this is my y, I guess I'm at 1, 2. And let's call that, I don't know, that point A. How about A at 1, 2? And then B, we're at negative 5, 2, so negative 1, 2, 3, 4, 5, 2. So that's B, negative 5, 2. And the question is if that's two sides of an equilateral, or excuse me, one side, two vertices of an equilateral triangle, how do I find the third side? And this is interesting because it looks like there's probably two options here, right? If I draw in that side, there it is. I could I can see that one way to construct the equilateral triangle would be up here. Another way to construct it would be down here. So it does appear that there are two possible solutions. to this analytic geometry problem. One thing we could do, but I won't, is rely on some symmetry arguments about where that I say third point C could lie. Since I'm trying to do it strictly analytically, I'll go ahead and use just only analytic tools. But certainly, if you were in a setting where you were free to use any tools, you probably want to use a line of symmetry here. Well, let's just kind of picture that point x comma y. It's either here or it's somewhere, about down in here-ish, right? And what has to be true about that point is these distances must all be the same as that distance in order for these triangles to be equilateral. Probably the first thing we should do is figure out what that distance. Well, it's a horizontal distance. This is at +1, that's at -5. So that means I'm 1, 2, 3, 4, 5, 6 units is the side length of the equilateral triangle in question. So we need this to be 6 and that to be 6. We need this to be 6 and that to be 6. And the question is where do those points x comma y lie? One prerequisite to finding the solution here is you need to know the distance formula if we're going to solve this just analytically. So the distance formula says the distance between any 2 points x1, y1, x2, y2 is given by this formula. X2 minus x1 squared plus y2 minus y1 squared. This is a common formula usually taught in middle school. It's also taught sometimes in high school geometry. But it's really just the Pythagoras' theorem applied to the coordinate geometry side. This would be the side length A, and that would be the side length B. I'll teach you a little bit more about this perhaps, or point you to some resources in the analytic geometry section of the course. But for now, let's just go ahead and use it. So what do we want? We want that point xy to have a distance 6, right? So this distance here we know to be 6, right? So we want the distance xy to be 6. So let's go ahead and talk about the distance from A. Let's call this C. And both of these points we'll call C, and the x that we get and the y that we get will give us 2 different C's, we hope. So let's see. Let's try the distance from from A to C. Okay, so if I go from A to C, then what I want is I want the distance to be the square root of the second point's x value, so that's just x, minus the first point's x value, so that's just 1, plus the second point's y value, that's just y, minus the first point's y value, that's 2. And we want that distance to be 6. Likewise, we want that point to have a distance from, let's say, B to C, that is equal to 6 as well. So let's see, from B to C, the second point's x value is just x. The first point's x value is -5, so it'd be minus and -5. The second point's y value is just y, minus the first point's y value, which is just 2. And that would be equal to 6 as well. So analytically, we can kind of now see that we've got 2 equations written in x comma y that are both equal to the same value, 6. So we should be able to use analysis, the rules of equations and algebra, to just set these 2 equations equal to each other and try to solve. So let's try that. So I'm going to say, therefore, why don't we come down here around the corner? So DAC has to be equal to DBC. Thus, we can set this equal to that. So we'll have the square root of x minus 1 squared plus y minus 2 squared equal to the square root of, let's call it x plus 5 squared plus y minus 2 squared. These are both distances. They're both positive square roots, so I can square both sides and not lose any solutions, I think. So let's try that. X minus 1 squared plus y minus 2 squared equals x plus 5 squared plus y minus 2 squared. I can see right away that I have a common factor of y minus 2 squared on both sides. So I'll subtract it from both sides, which will eliminate it. And we'll be left with a quadratic x minus 1 squared equal to a quadratic x minus 5 squared. We could absolutely, square root both sides at this point, I suppose. But I think that we have to be a little careful there because square rooting a square, of course, this could have been negative. Squaring it would make it positive. Square rooting it would, we'd have to look at cases where we either positive or negative both sides. Um, so I think it's probably safer just to square both sides. I'll have x squared, let's see, minus 1x minus 1x, so minus 2x plus a 1 on this side. On this side, I'll have x squared plus 5x, so 10x plus 25. I see an x squared both sides, so I can cancel that out. And let's see, did I make a mistake? Looks like 12, 24. Oh no, I think we're all right. Let's see what happens here. So we've got an x on both sides. Let's go ahead and subtract 10x from both sides. So if we subtract 10x here and subtract 10x here, what do we get? We get a minus 12x plus a 1 equals 25. If I subtract 1 from both sides, I should be able to get to this, negative 12x equals 24. So dividing through by negative 12, I get an x equal to negative 2. And indeed, this seems to be the obvious answer here, that the x coordinate of both of these guys is on that line because the x coordinate is negative 2. Does everybody see that? I wish I could hear you all say yes. But that, seems like the obvious answer, and maybe you would have, right off the bat said, well, there's a line of symmetry here, so I would just find, the average of negative 5 and 1, which of course is negative 2, and that's going to be the x coordinate, and then solve for a y coordinate. So, but we're sticking to an analytic approach, so the equations do indeed back up, I guess, the symmetry, the transformational aspect that we'll see next. But let's go ahead and solve now for the y value. This should be more interesting, right? Because there should be two y values that emerge. And so we know x, so we can go back up and plug into either one of these two equations our result for x, and that will give us an equation in y, which should allow us to solve for y. So I'll plug into the first equation, the distance AC, and let's see what we get. So we have the square root of x minus 1, so it would be negative 2 minus 1, quantity squared, plus y minus 2, quantity squared. I'll just say, and that's equal to what? 6, right? Okay, we're trying to get at y, so I think we got to undo the square root. Let's square both sides. I'm going to clean this up a little bit. Negative 2 minus 1 is a negative 3 squared, plus y minus 2 squared equals 36 now when we square both sides. Negative 3 squared will give us a 9. So let's see if we get a 9 here. Let's see, so 9 plus y minus 2 quantity squared equals 36. Let's go ahead and subtract 9 from both sides. And we'll get y minus 2 squared equals, let's see, 9 from 36 is going to give us 27, right? 16, yeah, 27. I don't know if I can get my, sorry, my lead is out. Okay, there it is. I got my lead back now. Okay, so we're at this equation, y minus 2 squared equals 27. Now you kind of have a choice here. You could square this out and solve the quadratic by setting everything equal to 0. Maybe the quadratic formula would be a useful tool in that point, at that point. But I think it's easier to see that, well, this is a square. I can undo a square by square rooting both sides. So that's what I'm going to do next. So let me copy over where I'm at. I'm at y minus 2 quantity squared equal to 27. So that means y minus 2 will be the square root of 27. And here's where we got to be a little careful. If something squared is equal to 27, that something could be either positive or negative. So here's where your plus minus will come in, right? Because either squaring either positive root 27 or negative root 27 will yield a positive 27. And then the last step, of course, would be to add 2 to both sides, and we get 2 plus or minus root 27. Let's see what root 27 looks like. 27 raised to the 0.5, what do we get? 5.1, well, 5.2-ish. So this is sort of y is approximately equal to 2 plus or minus 5.2. So you can see that there are actually two values here, right? So y1 would be equal to the 2 plus the 5.2, or 7.2, and that's an approximate notation, right? And y2 would be approximately equal to 2 minus 5.2, and we're going to get a negative 3.2, right? And so what that means, I guess, putting everything together, you know, this location right here is about 7.2, and that location right there is about negative 3.2. And it kind of makes sense, right? Because if I start at 2, you know, which is the altitude here, then I'm either adding or subtracting a value from that mid value of 2 to get to the, you know, the upper and the lower possibilities for the vertex. So putting it all together, we could say 2 vertices are possible. They are what? It's either negative 2 comma 2 plus root 27, which we could also, you know, I didn't even think of this, but we could actually, we could simplify root 27, right? That's 9 times 3, so it's the square root of 9 times the square root of 3, so 3 root 3 would be one way of writing root 27. Either one's fine for me. 2 plus, let's see, 3 root 3, or negative 2 comma 2 minus 3 root 3, which is in approximate notations, this is about negative 2 comma 7.2, and this one's negative 2 comma negative 3.2. So those are the two vertices that are possible in this setting, which is, of course, an analytic geometry setting. You know, if you think about it, you know, when you compare the work that we did here to create an equilateral triangle using just primitive notions of point, line, circle, and logic, compared to the kind of work that we do here when we're on the coordinate plane, asking questions about distances using x's and y's, you can certainly see that it's a very different flavor of activity. I guess let's go ahead and move on to the last piece. So what do I want to do? Escape. There we go. The last question is, okay, can you identify line and rotational symmetries of an equilateral triangle? So let's go ahead and take a look at that idea as well. Okay. I guess to do this, what I'm going to do is I'm going to create a little manipulative. Suppose I get an equilateral triangle drawn, so let's draw one up really quick. I'm going to use my knowledge of constructing the equilateral triangle here. Okay, so I got one drawn up. And then what I want to do is I want to kind of poke some holes in this guy to draw, I guess I could just use this, right? To draw one up underneath it that I could cut out. So let's see if I sort of poke through here, and poke through here, and I poke through here. Then I should be able to use those holes to draw up an exact copy of the one I had before. And I'm going to go ahead and cut that puppy out. Get this thing cut out. So the reason I did that is I wanted to use something to show you that transformational symmetries are, of course, the idea here is movement, right? So I'm going to go ahead and color this guy up really quick just to make it clear who's on top and which one's being transformed, I guess. All right. So let's talk about rotational symmetry first. So rotational symmetry would say, is there some point that I can hold fixed and then rotate the figure about that point to get back to the figure itself? And I think there is. It's somewhere right in the middle here. That if I hold, a point right in the middle fixed, that I can rotate this guy and get it back to itself. And the question is, what angles of rotation will I have to do that? And I think it's fairly straightforward, that it seems like, well, if I kind of think of these as lines emanating, that this point has to go to that point right there, if I hold that middle fixed, and this point would have to go to that point, and this point would have to go to that point. So we're taking this 360-degree circle, and we're splitting it into three angles of equal measure. So it appears that if I take 360 and I divide it by 3 to get 120 degrees, then an isosceles triangle, equilateral triangle, it certainly has 120 degree rotational symmetry. But I also noticed that if I do it twice, if I go once and then twice through that important middle point that I don't seem to be able to. So let's try once and then twice. That would take sort of one here and the next one here. So I could double this as well. Sorry, I'm having pencil troubles today. So it certainly would have 240-degree rotational symmetry as well. Now I could also do it 3 times, of course, once to there, and then that same point over to here, and then that same point up to here. But if I kind of mark that point just to keep track of where it's going, if I do it 3 times, then it goes first to here, 120-degree rotational symmetry, then to here, that's 240-degree rotational symmetry, and finally back to here, which is 360-degree rotational symmetry, and I'm really back to myself. And so we don't really think of that as a, telling us anything, because of course any figure, if you rotate it 360 degrees, will return to itself. So these are the only two rotational symmetries that an equilateral triangle has. Okay, now let's talk about reflective symmetries. Okay, I have here, a mirror that you can use to analyze reflective symmetry. And what I'm going to do is I'm playing around with the mirror in terms of trying to see if there is a line of symmetry. And I hope that you can kind of see that. I know it's hard to see from above there, but as I open it up, can you see that the reflection there appears to be exactly an equilateral triangle? So I seem to have found a line of reflective symmetry that's right through the middle there. I wonder if I can hold it in place and just, this is really hard to do, draw that in. So that would be one line of symmetry, and it seems to stand to reason that that would be true as well from this vertex. I don't know if you can see that, if I can turn it a little bit. Um, and I probably need to, if I move it to about right there, I seem to be getting a nice line of symmetry there as well. And finally, it looks like there would be one right here. And interestingly enough, it seems to go right through that point where the other two lines of symmetry. So it appears there's 1, 2, 3. So I'll name them here: line 1, line 2, and line 3. And I'll just say 3 reflective symmetries in the lines marked L1, L2, and L3. So certainly a different view of the equilateral triangle, a transformational view. If we kind of step back and think about it from a teaching standpoint, you know, some of this seems to be at play in terms of the line symmetry here of the analytic exercise. As far as symmetries here, you know, I guess I think you can kind of get a sense that there's some symmetry going on in the construction because of the fact that the two arcs have exactly the same radii. But I'm not certain there is as much going on there in terms of how these bleed over one into the other. But certainly a different view of, you know, properties and useful, I guess, information about this object, an equilateral triangle. Okay, I'm almost done here. I want to spend just a little bit of time now talking to you about technology, and we'll end here. You know, one of the things that's really changed the landscape of teaching geometry in the last 20 years is the rise of the availability of dynamic geometry software that allows for the integration of synthetic, analytic, and transformational perspectives of shape. And so I want to show you, you know, how these three perspectives come alive in technology in a setting that's technologically dependent. So this is the software GeoGebra. Those of you who are coming off our technology course are probably have had some introduction into this. If you are new to GeoGebra or new to our program, you'll probably want to go ahead and get a copy of this and get started familiarizing yourself. Please email me if you need pointers in the right direction, and I'll make sure and add to our course webpage some resources on GeoGebra, some users manuals and whatnot. But to find GeoGebra, it's very easy to do this. If you just type in GeoGebra into a Google search engine, it'll come up as the top hit. If you go to the page on GeoGebra, this is the page. Here's the download. If it's basically it's a freeware software, and you can get it for Windows, Mac, or there is a Chromebook version as well. I do prefer the desktop version to either the Mac or Windows desktop version. So that's a little bit about how you can get it. And let's talk about what it gives us. So for example, if we were trying to construct an equilateral triangle, I would pick the segment tool. And by the way, if you hold this little red arrow down, you get a whole suite of tools that are associated with segments. So that would be all the lines. You know, you can have a line, a segment with a given length, array, polyline vector, vector from points. So all the line tools are nested under, you know, this push button, and whichever one you used most recently will appear, you know, at the top of the list up here. So I'll pick the segment button, and I'll just draw in a segment A to B. Now let's say we're just teaching a course that's highlighting synthetic geometry. Well, then you might ask students, you know, to build, you know, create a triangle ABC such that, you know, it always maintains its the property of being an equilateral triangle. Well, that would just be, you know, a recreation of exactly what we just did on paper. I would choose the circle tool, and by the way, all the other circle tools are listed here below in the drop down. But I'd put my compass in effect, on A and draw a circle with radius AB. I'd put my compass in effect on B and draw a circle with radius BA. And I'd see that I have two locations for selection for this point. I'm going to go ahead and put both of them in just because I think it's kind of interesting. But I'll go ahead and build the polygon here, 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 and here. So I picked my polygon tool. Of course, there's a bunch of polygon tools nested underneath the polygon. And what's interesting about this is that we've created something that looks a heck of a lot like what we did on paper, but the big difference here is that this thing is dynamic, right? I can grab A and B, and of course it moves all over the place, but because of the way that the points are defined and the circles are defined, that everything's dependent upon the length of A to B. So adjusting A to B, of course, makes things all adjust in turn. What's kind of neat about this is that you can hide things. So I could take this and under here you could excuse me. I guess if you just right click on it, you can. What do I want to do here? I want to hide this thing. I guess I'll hide it over here. You can also push the aerial button there and hide it, and the aerial button here and hide it, so the circles are hidden. I'm going to leave that point D out there just to remind us that that's the other point that could have been used to define. So we have like a really nice dynamic synthetic view of an equilateral triangle. And what's neat is that we can just immediately jump to the analytic view of the triangle by just, if you click on white space here, then you get these choices, and the axes, which are default hidden, come alive. And that's the reason why all of these labels over here, which are of course analytic views of these objects, points as x comma y's, circles as equations, segments with lengths, these things all come alive now when they're on the coordinate plane. And of course, it's kind of nice if you're working in an integer setting to add, I guess, a grid, because then things snap to a grid like this. So I could go up here and I could put my point B on the point 1 comma 2. I could put my point A at the point negative 5 comma 2, and I could take a look and see that sure enough, the point C, which was the point that we decided above the x-axis that would be a point for of interest for an equilateral triangle, is negative 2 comma 7 2, and the point D, which is now you realize why I kept it, the point that could possibly be below, is this point negative 2 comma negative 3.2 in the third quadrant. So a nice way to check, for example, the results that we got analytically using dynamic geometry software. Let me blow this up a little bit more. So that's kind of a nice tool, I think, because it gives you, with the click of a button, a switch from a synthetic view to an analytic view of geometry. The last thing I'll say is that, I'll go ahead and get rid of these again, is that, and I'll go ahead and get rid of this, is that it also allows you to analyze transformation. All of the transformation objects are under here, the fourth from the right. I'm going to go ahead and reflect something about a line. To do that, I'm going to add a line in here first of all. And what I'm going to do is I'm going to just put a point out here, and I'm going to reflect that point in the line. So it says select an object and then a line of reflection. So I click on that, I select this object and a line of reflection. Oh, didn't work, did it? There, sorry. Let's try this. There it went. And it takes G to G prime. And of course, this thing is dynamic, right? So if I move this line, of course, the point G moves all over the place. And what I'd be interested in looking at is, well, what if I find some sort of line of reflection? Now, I'm pretty sure that line of reflection is the line that's defined by this point and the midpoint of this side. But I'm just going to sort of, play around with this. And if you can see, as I move this point around the equilateral triangle, it does seem like, indeed, it is reflected. Now, whether or not I'm actually on the midpoint is another question. So we could do something like that. We could say, well, what's the midpoint of this side? Let's try midpoint or center. Boom, boom. And then we could move this point onto H, or even better, there is an attach tool. Let's see if I can move it. So the attach tool says click on a point and an object to attach. So I'm going to click on that point, and I'm going to click on, oops, maybe not. Maybe I have to go back the other way. Let's try it again. I'll click on that point and attach it to this object. Oh, that didn't work either. Okay, well, let's just go ahead and delete the line. You're watching me fuddle through this. I'm sorry. And let's go ahead and get out of here. I'm going to delete that and this, but let's go back to our what we think is true. We think that the midpoint, let's go to midpoint of these 2 points. There it is. If we make a line there, that's the line of symmetry. And let's just see if that's true. I'll put just a generic point out here, and I'll reflect it into this line. There it is over there. And now if I move F around, I should be able to see that it is indeed mapping just like it should, right? It's reflecting all those points on that side to where they seem to need to go, all the points on this side where they seem to need to go. Of course, everything on the midline just gets mapped to itself. But even like these points on the interior, it's mapping them perfectly across. And it doesn't really matter, of course, where I put the triangle itself, but it's a really powerful tool, I think, to come to a pretty good conjecture that the line of symmetry on an equilateral triangle is any vertex in the midpoint of the side opposite that vertex. So those are the 3 lines of symmetry because there's 3 vertex and 3 midpoints. So I hope that gives you a good sense of the power of dynamic geometry to help you form conjectures or help students in your classroom understand concepts. I'll be using this in a lot of my lectures, and you're certainly welcome to use it in your homework. It's not required, but I would think it would be a nice tool for you to employ. Okay, well, that's about it for this first lecture. I've certainly talked enough, 45 minutes. I look forward to seeing your work on the content exercises, and please do let me know via email or if you have any questions or concerns.